The new chapter, chapter number 9, is areas of parallelograms and triangles, which are going to deal in today's session. Parallelograms and triangles. We have dealt with various properties in quadrilateral, special type of quadrilateral called a parallelogram and a triangle. Now comes the deep investigation on areas of parallelograms and triangles. Today's session is about investigation of triangles and parallelograms with their areas. Before we get into the areas of parallelograms and triangles, let's come with the introduction. Introduction. Let's recap with geometry. We have previously come out with the concept of geometry, which was referred as geo plus metry. That is, geo stands for earth and metry stands for measure. So measure of earth or measure of the agricultural fields or measure of the land is what from which geometry has originated. So this problem was existing in prehistorical facts that many agriculture fields or lands were supposed to be divided among the children or the next ancestors. So division of land to be done equally among all the sons or daughters was a difficult task during those times. So geometry was very much in use during those times. In order that the land be divided equally, many of the people used mathematics proudly. So here comes the introduction of measure of earth connected with areas of parallelograms and triangles. To continue with, imagine I have an agriculture field which is triangular in shape. Imagine this is my plot and this is the plot of land which I want to divide equally among three people. Like for example, say Budhia was a farmer Budhia wanted to divide his triangular piece of land into three parts so that he wanted to distribute the land for his two daughters and one son. So how can he distribute this triangular piece of land equally to the two sons and one daughter without any disputes? This to be done mathematically. So such problems give us an indication that we need to give more importance to areas of triangles and of course areas of parallelograms. So here Budhia has tried to cut his land out here and then he tried to cut his land from each corner to some part, estimated part in the middle. He wanted to cut his land in this region. Now after cutting his land into three parts in this manner, he wanted to give this to the first piece to his first son, and this piece of land to his second son, and this piece of land to his daughter, who is third in number. Now he assumes that these three areas are equal. According to Budhia, his estimation that from the center of this, approximately the cutting of the land to each of his vertices of his agricultural land, A, B, C, are assumed to divide the whole triangular piece of land into three parts, first, second and third. And according to Budhia, area of the first piece is equal to area of the second piece. Though they are in different shapes, it is assumed that area of the first piece, according to Budhia, is equal to area of the second piece, and also this is equal to area of the third piece. Is how we understand each of the areas being equal. Thus, the two sons and the daughter would happily share the land without any disputes. But here the biggest question comes: how do you prove mathematically that these three are equal? Is it that they are just convinced that they are equal without any proofs and justifications? Or is it that really Budya could justify the three pieces of land exactly in equal areas? Here comes the investigation in mathematics about how we can find the areas of equal pieces within the triangle. Is how we are going to connect in the future coming topics. Budya's problem related with area of triangle subdivided into areas of three different pieces of triangles. Now that we have investigated on Budya's case of a triangular field arising in to the conclusion that we need to give importance to areas of planar regions or areas of regions, mostly the lands, without any dispute. Now comes, what is area? How do we define area in the branch of mathematics? So let's see in today's session about area and its mathematical properties. So here comes area. What is an area? So let's see in brief area. Now imagine I have a closed region. I have a closed region. So this region is closed in all directions. So such a region which is closed in all directions is called a planar region. This is a planar region. So this planar region has area, which is called the magnitude or measure of this planar region is called area. That is the entire boundaries within whatever region is covered, we call that as magnitude or measure of the planar region. So in simple manners, area is defined as the magnitude or measure of the planar region. Is called area. Is how we define area of the planar region. A close-sided figure whose magnitude or measure which accounts to area. The magnitude or the measure of the planar region is how I define area of the given region. Area of triangle, area of parallelogram, area of quadrilateral, and area of various other things is how we understand. The magnitude or measure is always expressed in a number. That is, the area, which is the magnitude or measure of planar region, is generally given in count of numbers, and the value of the number will define the size of the area. So this is a very important note. The area is generally counted on numbers. That is, area equals 3 centimeters square or area equals 15 centimeters square, etc. Now here this implies that if the area is 3 centimeters square and area is 15 centimeters square, that means the second area is bigger than the first area. Is how we estimate the magnitude or measure of the planar region through the value which is assigned to the area. And these are the units given for area. Is how we understand the area connected with the planar region. Now that we have discussed about area connected with planar region, now comes congruency of two figures. If I take two planar regions or two closed figures, let's see what congruency stands. Today's session is about congruency of two figures. So let's take two figures. Say I have a figure and this figure too. Now I have two figures out here, this being in this manner and this being in this manner. Now the question comes on defining congruency of these two figures. What is congruency of these two figures? Congruency of two figures, these two are said to be congruent. This is figure 1 and figure 2. Both the figures are said to be congruent if they have same shape and same size. Imagine this is in this form, and if I rotate this to the top, also it has the same shape. This is indirectly understood to be in the form is how I understand this in this form. So this connected with this when this is rotated into this. So this is exactly the same as this. So congruency of two figures is when they have the same shape and of course the same size. So here I define two figures are said to be congruent if they have same shape and size. Is how we define the congruency of two figures. Two figures of same size and same shape are said to be congruent. This is congruent to this. But this is not congruent to this because they are of same shape but they are not of same size. Since not of same size. Since they are not of same size. Therefore, this is being of smaller size and this being of bigger size, though they are of same shape, cannot be congruent. Is how we understand the congruency of two figures connected with same size and equally same shape. Now that we have defined the congruency of two figures, now let's see how we can connect congruency with areas. Two figures are said to be congruent if they have same shape and same size. Then what will be the status of their areas is what we are going to define in today's session. Congruency connected with areas. Now that we have defined congruency, let's recall the definition. Congruency is connected with same size and same shape. Now it is generally assumed that if two objects or two figures are of same size and same shape, mathematically it is proved that they must be of the same area. So here comes the conclusion that if two figures are of same size and same shape, then mathematically they must have the same area. That is, the measure of their planar region or the magnitude of their planar region must be same. Is how we define the property. Therefore, when two figures are congruent, not only did they have same size and same shape, they have same area. So I come to the conclusion that two congruent figures have same area, is how I conclude the statement. Two congruent figures have same area is the learning outcome, and congruency connected with areas. Now that we have connected areas with congruency, let's come with the converse of connecting congruency with areas in a similar manner. So what does the converse say? The converse is about if the two areas are equal, will the two figures be congruent? Because in the previous session we have seen that if the two figures are congruent, then their areas must be equal. Now the question comes, if the areas are equal, will the two figures be congruent? Let's investigate the congruency of two figures connected with areas. As converse. So my question here is, if the two figures have equal areas, then will the two figures be congruent? Is the biggest question out here. So let's investigate this. If the two figures have equal areas, then will the two figures be congruent? So imagine I take a triangle whose area is, say, 12 centimeters square. And imagine I have a parallelogram whose area out here is also 12 centimeters square. Now clearly we know that the area of the triangle is 12 centimeters square and area of the parallelogram is 12 centimeters square, and therefore the areas are equal. So I find the areas to be equal for both the triangle and the parallelogram. But are they congruent? Let's see if triangle is congruent to parallelogram. The congruency concept says that the two figures are congruent if they have same shape and same size. Now here comes the question on the triangle and parallelogram have same size because their areas are same, but are they of the same shape is also very important in ruling out for the congruency. In justifying the two figures to be congruent, we have to justify on same size. Yes, of course, they are of same size, each size being 12 centimeters square, but are they of the same shape? No, this is a three-sided figure and this is a four-sided closed figure. So they're not of the same shape. It fails with the second case. This is a three-sided figure and this is a four-sided figure. Therefore, they are not of same shape, but they are of same size. Therefore, I come to the conclusion that if the two figures have equal areas, as in the case of triangle and parallelogram, then the two figures may not be congruent. Not always. They are congruent if it satisfies with the condition that the two figures have the same shape. Failing with the condition here, three-sided and four-sided figures can never be of the same shape. Therefore, my learning outcome or the conclusion out here is that two figures with equal areas need not be congruent. Congruent. Is how I conclude two figures with equal areas need not be congruent. Is the conclusion in the converse. So the converse of the congruency statement says that two figures which have equal area need not be always congruent, just in the case of triangle and parallelogram. Now that we have defined area of any planar region and connected with congruency of two figures in brief, now let's see how we are going to represent area, because we're going to solve many problems where areas are involved. Now comes the question on how do we represent area of a closed region. Representation of area is the session about. Representation for area. Now let's take this is the region, say, of the planar region. Now I would like to find area of this region. Now how do we represent this region with area? If this is represented by A, this whole region is represented by A, then area of region A is denoted by area of A or AR of A. So simply when I write AR of A, that implies it is the symbol or representation for area of A. So area of region A is denoted by AR of A. Similarly, if I take a triangle ABC and I take the height and the base to be 5 and 2 centimeters, then to find area of this triangle, for example, with altitude as 2 centimeter and the base is 5 centimeters, then area of triangle ABC is denoted by area of triangle ABC. Is how I denote this. Area AR of triangle ABC implies area of the triangle ABC as denoted with this region. Is how I understand area of the region, which is nothing but half into base into height, 5 centimeter square. Therefore, area of triangle ABC is 5 centimeter square. Is the representation when you find area. Finally, I represent the answer with AR of the given region. This region is triangle ABC. This region is A, which comes here. AR of A implies area of the entire region A. Is how I understand the representation for area of any given region. Now that we have defined the representation for area for the region A being AR of A, let's see how we can connect this with congruency of two figures. So as the representation is understood for this region A, I have the property which says for congruent figures A and B. Say I have two regions A and B which are congruent. For those congruent figures A and B, I understand the property as AR of A is equal to AR of B. Is how I understand the congruency. For congruent figures A and B, AR of A equals AR of B, because when two figures are congruent, their areas are equal, their sizes are equal, their shapes are equal, and hence AR of A equals AR of B, the representation of area for congruent figures. Now that we have defined the representation of areas, now let's see how we can connect non-overlapping planar regions connected with the areas. Suppose we have non-overlapping planar regions. The session non-overlapping planar regions. Let's see what are non-overlapping planar regions. Now here, the word overlapping in the sense trying to join the two planar regions without overlapping each other. So let's see in brief the non-overlapping planar regions. For example, I have these two regions which are separated here. So I have two regions here. This is region A, which I denote with say some P, and this is region B or region Q, which I denote. So I have two regions here. This is region 1 as denoted by dots, and this is region as denoted with this. Now I have two regions. The first region region 1 and this being region 2. Now these two regions are joined together such that they do not overlap. Now the planar region 1 denoted by P and the planar region Q denoted by planar region 2 denoted by Q are now joined together, where the whole region joined is denoted by T. If T is the total planar region, if T is the total planar region which joins both P and Q, which joins both the region 1 P and the region 2 Q without overlapping. One of the most important thing is that the planar regions do not lose their area when they are joined. They are non-overlapping. So this plays an important role. Without overlapping each other. Now here T is the total planar region which is obtained by region 1 plus region 2. Then I have a mathematical property which connects area of the whole total region T denoted by AR of T will be equal to area of the region P, that is the first region, plus area of the second region Q. So if I join the two regions, implies area of P plus area of Q equals area of the entire total region T. Is how I understand the total region. Area of T equals area of P plus area of Q. So T the total region which joins both P and Q, then area of the total region will be area of the two regions which are joined without overlapping each other, which plays a vital role. Non-overlapping planar regions denoted with mathematical equation AR of T equals AR of P plus AR of Q is how we understand the concept connected with planar regions. Now that we have discussed about planar regions and their areas, now comes the areas connected with different geometrical properties. Mostly we will see the figures which are on the same base and between the same parallels. That is, if I observe and investigate the two objects which are the two figures which are on the same base and between same parallels, then what is the conclusion or the mathematical outcome which is made by investigating the figures between the same base and between the same parallels is what we are going to see for today's session. So today's session is about figures on the same base and between same parallels. So let's see in brief the figures on the same base and between same parallels. For example, let me take an example case. Say I have the same base AB. Now as the concept says about same base, let me take the same base AB and let me take the two parallel lines with the base. So I have a parallel, this is parallel to this. So I have a line L which is parallel to the base AB. Now it says that any figure you take on the same base and between same parallels will have certain geometrical properties. So let's see what are the geometrical properties connected with two figures on the same base and between same parallels. For example, let me take a triangle which connects out here. Suppose I draw a triangle with the base AB, and let's see the figure 1 which is obtained by drawing a triangle. Let C be the point from the parallel line where a triangle is formed. Let me take another point D where I would draw a triangle provided with the same base. So between the same parallels AB and the line L, I have a triangle ABC with the base AB. Now I will draw a triangle ADB with the same parallel. Now here comes the investigation on what would be the relation between this triangle ABC and this triangle ADB. So here we are going to investigate the figures on the same base and between same parallels. So in this case, triangle ABC and triangle ABD are the figures on the same base and between same parallels. So triangle ABC and ABD are said to be the two figures or the two triangles on the same base and between same parallels. Here AB, which is the same base for these two triangles, and the parallel lines are the base AB, which is parallel to the line L, is how we see the parallels. So these are the two figures, for example, when I take are the two figures between same bases and same parallels. So triangle ABC and triangle ABD are the figures on the same base and between same parallels. Is how we can take many examples in mathematics where we can take two figures between same base and between same parallels. This being one of the example. Let me take another example to understand the concept more better, to be continued with. Now here, let me take the base AB and let me take a line which is parallel to this. Now AB is the same base, and let me take two points C and D, where ABCD is a parallelogram, and let me take a point E such that there are two figures formed between the same base AB and between these two parallels, that is, one of them being this parallelogram and this being a triangle. So ABC is the triangle and ABCD, ABE is the triangle and ABCD is a parallelogram, which are on the same base AB and between the same parallels. So here AB is the same base and L is parallel to the common base AB, then triangle ABE and parallelogram ABCD are the two figures which are on the same base and between same parallels. So here note that this and this are the figures on the same base and between same parallels. This is how I understand the concept of two figures with the same base and between same parallels. This being one of the example case. Triangle and a parallelogram on the same base and between same parallels. Now let's take an example case where the triangle or the two figures are not between same parallels to understand the concept more better. For example, I take the same base AB and I take a parallel line L which is parallel to this. Now here let's connect say I have a point C which makes the region ABC. This is one of my region. Next comes say another region in which I have a point D which connects with B. With this. So have another triangle with the shaded region out here. So here let me say I have a point D which is exactly out here. Therefore, I have a point D which is down this exactly but not touching the line L out here, the line which is parallel to this. So in this case, I see that the triangle ABC is on the same base AB and triangle ABD also is with the same base AB, but they are not between same parallels because ABC is a triangle between parallels with the third vertex C exactly on the parallel line. But this point D is not on the parallel line and hence it is slightly below. This region cannot be between same parallels. So I come to the conclusion that since point D is not on the line L which is parallel to AB, therefore though the two figures triangle ABC and the second figure triangle ABD, though triangle ABC and triangle ABD are on the same base, are not between same parallels L and AB, is how I understand this exclusive problem. Triangle ABC is between the same base and between the same parallels, but triangle ABD is on the same base AB but not between the same parallels. This region is left out, is how I understand that the two regions are said to be between the same parallels if their remaining vertices other than the base entirely lie on the parallel lines. So here the remaining vertices other than the base here is C, so this must entirely lie on the line L, which is parallel to AB. Here the remaining vertex D other than the base AB must lie entirely on L, but since the point D does not lie on the line L, which is parallel to AB, therefore it is not between same parallels, but it is between the same base AB, is how I understand the two figures are on the same base and between same parallels if the figure has its vertices other than the base which lie entirely on the line which is parallel to the base, is how we conclude with figures on the same base and between same parallels. Now that we have defined and understood two figures on the same base and between same parallels, now comes the discussion of using the two figures on the same base and between same parallels for the learned concepts. I'm talking about the parallelograms. So let's investigate on the two parallelograms which are on the same base and between same parallels. Let's see what would be the learning outcome or the conclusion drawn out of the investigation. So today's session is about parallelograms on the same base and between same parallels. Parallelograms on the same base and between same parallels. So let's take the parallelograms on the same base and between same parallels. Let the base be AB out here. Let there be a line L which is parallel to the base AB. Now here, let me take two parallelograms. This is the parallelogram on the base AB, say C and D. Let me take another parallelogram. E and F. So here I have two parallelograms. One is the parallelogram which is obtained by ABCD. is the parallelogram, and the other parallelogram is this. Out here. So the two parallelograms are ABCD and ABEF, which are on the same base AB and between the parallel lines L and AB. So here figure ABCD and figure ABEF are the parallelograms on the same base and between same parallels. Are parallelograms on the same base and between same parallels. The same base here being AB. And the parallel lines are L and AB. So let's see what is the property which connects the two parallelograms ABCD and ABEF, which are on the same base and between the same parallels. Property which connects is parallelograms which are on the same base, and between same parallels are equal in area, is how I understand the property. The property says that if the two parallelograms lie on the same base and between same parallels, any two parallelograms lying between two parallel lines and lying with the same base must be equal in area. So area of this parallelogram is equal to area of the second parallelogram in this diagram, is what is the property which defines in mathematics. So area of this parallelogram, therefore area of parallelogram ABCD is equal to area of parallelogram ABEF, is how I understand the area of two parallelograms being equal when they are on the same base and between same parallels. This holds for any two parallelograms using the two properties connected.